Good morning, everyone. My name is Audrey Goulven. I'm representing a company called Dassault Systèmes. Very pleased to be here with you today. I'd like us to explore how we can innovate together to deliver nuclear at scale and to rise to the challenges ahead of us. And why innovate? Why do we need to rethink large-scale nuclear project delivery? Because till now, the way we deliver nuclear project is still attached to a very traditional, fragmented approach with bespoke, quite slow delivery models. And we are still facing delay, schedule slippage, cost overruns, late decision taken, and some rework aspects. So we are in a context also where nuclear projects are obviously facing increasing challenges related to a rising systemic complexity, regulation demands, data-driven control, and predictability. We know industrialization modularity will be part of the answer to next-gen nuclear projects, how we are going to deliver that. But what we are lacking is embracing digital innovation at scale as well and transform those traditional segmented approach to deliver a project into a more integrated, orchestrated one with digitally enabled programs. What does it mean, digitally enabled programs? For us at Dassault Systèmes, it means embracing greater digital innovation and especially a well-proven technology which we call virtual twins. A virtual twins, what is it? It's not a 3D static model only focused on the nuclear plant or the nuclear asset. It is a scientific, dynamic representation of the reality, capturing not only the asset itself, but the processes, the people, the performance, and all the data that allows this asset to be designed, built, delivered, and operated. And this is already used in nuclear sector. It is starting to be embraced more and more, and the transformation is already ongoing. The value of the virtual twin is to aggregate this data, which is very siloed today and very fragmented in different systems, across the supply chain, across different stakeholders, and transform that into contextualized data insights that would lead to actionable decisions. That's the purpose of the virtual twin, help people understand the complexity of the reality around them and predict what the future would look like. So what is the decisions that we need to make right now and why we are taking those decisions as well. And the twins are really generating from this data scattered everywhere new knowledge and know-how that will bring value to the full ecosystem of the nuclear programs and across the supply chain and the life cycle as well. Let's start with something which is quite major in nuclear projects. It's the systemic complexity which is attached to it. We are not just talking about a nuclear plant. We are talking about an ecosystem of very complex interfaces, multiple systems interconnected with each other, and multiple stakeholders responsible for them. So what's key through the virtual twins is to maybe start with what we will call model-based system approach, and especially what we call a system of system virtual twins. Why? Because model-based system provides a backbone that connects all the domains, and you will see that through an illustration just in a few minutes. Whereas a system of system approach expands this visibility across the entire life cycle, aligning governance, integration, and adaptation, and bringing all the stakeholders on board. And this is unlocking significant element of values because capturing all those interfaces and interactions early stage, we can anticipate and assess risk and impacts beforehand, before starting any construction activities. Globally, we can tackle regulatory, logistical, technical, human challenges. We can optimize the performance. We can go through more resilience in terms of global program organization and program delivery organization. We can think about industrial scheme that we want to implement to tackle the challenge of the supply chain disruptions. And we can ensure full traceability from concept to commissioning. This is a dynamic modeling exercise that allows us to be more predictive and more adaptable to what's going on in the future. This is what it looks like. So within the Fluid Experience platform, which is a platform where the virtual twins deliver what we call experiences on sovereign cloud, if necessary, we can see here a global architecture of what is the ecosystem of a nuclear project, meaning not only the system of interest, which would be the plant itself, plant breakdown structure, for most of you are very familiar with, but all the stakeholders around it, the physical interfaces, the regulatory aspects, and bringing all digital continuity and traceability between all those different human stakeholders and technical interfaces until the definition of work packages that would allow us to deliver. So here you see all these interfaces mapped through this dynamic model, which is not a static, again, representation of those interactions. You can see the interfaces between stakeholders, meaning what is the collaborative processes that are connecting one to the other. What is the plant breakdown structure attached to this in terms of technical perimeter, functional, physical interfaces at plant level. And we can go beyond our presentation, having a deep down in the work breakdown structure itself, looking at the work packages, but also looking at the companies that are in charge of those work packages, doing the proper assignment of the work packages for a specific area and discipline to a dedicated company. I can look at the interface within one area, one building, from engineering to construction, assembly, installation. But I can also capture the interactions of that building with the geographical interfaces in my plant with other buildings, which would give me a global understanding of the operational delivery model without even speaking about 3D model yet. It's all about system thinking, system modeling. Here I can do, because this is a living dynamic model, simulate any impact of change. And that's the value of this living model. I can simulate for a specific player an impact on a delay on a work package that is submitted. I can simulate disruption on supply chain and delivery model. And I can then anticipate on the future risk that I will be facing in the phase of my project, even before, again, a shovel hits the ground. And now, moving from this MBSE system of system approach, still in the preparation phase of the project, most of you know, I'm sure, what we call advanced work packaging approach. Well-known methodology, which we think is indeed really fitted for the complexity of the nuclear at scales. But what's interesting within the virtual twin is if you combine MBSE with the AWP approach. MBSE defines what to build and why, which I showed just before, the system logic, the function, the interfaces, whereas AWP defines how and when to build in a structured, safe, and efficient execution. So because of the virtual twin, we have now a model-driven AWP process that is replicable. And all the models I showed before have created a repeatable, consistent methods and methodology that will be replicated on projects, on fleet deployment for SMR, on other large-scale power plants. Using these models, combining it with AWP within the twin, we have the capability to optimize, obviously, the scheduling of the works that is coming ahead of us, so testing multiple scenarios, what we call what-if scenarios. We can run 4D simulations, you see that, on maybe high-risk areas. And we can, again, because of the complete digital continuity and traceability, make sure that any impacts is anticipated because I'm going to directly assess what will be the consequences on the global program because I've got the dynamic model in place before. So this accelerates standardization and obviously de-risk construction in a very early phase. This digital thread from design to execution is allowed and enabled thanks to the virtual twin approach. This is how it's going to look like. We start with the 3D model here, because now we are talking about preparing the sequencing of the works. So we have the division of the what we call CV works areas, as per the AWP approach. But we have the same architecture and model that connects all the work package together, from engineering, procurement, system, and construction. And this is all the links between them enable us to move from building an engineering BOM to construction BOM to the indeed work plan. And from that, we can go into then the 4D sequencing of the works. But not only to phase the works in a very static manner, but again to have a dynamic approach about the sequencing and the construction, simulating any impacts on the delay, for example, or change in design. How would that affect the sequencing of the construction I've foreseen? So this is bringing flexibility and reactivity into it. And this is also allowing, as I said, 4D simulation on high-risk areas, not only simulating, as you can see here, a simple installation of an equipment on a roof, but also considering the multi-physics simulation and parameters that are behind it, meaning the stress on the anchors of the crane, how the crane is indeed operating in reality, what is the dynamic behavior of my equipment on a truck in the face of transportation. This is all part of what the twin can offer in terms of simulation. The other aspect when we speak about deployment of large nuclear projects being, again, large nuclear plants or SMR is the constraints related to the sites. And this is why often it's not enough to look at the model of the asset itself, but considering its contextualization in the context of the site, of the environment, is bringing additional value to the players. You are an owner-operator, you want to deploy a large-scale program, you have to do some site selection. How do you compare based on, let's say, a first rough idea of what the power plant would look like without having chosen the technology yet? How are you going to do that? And again, with the twin, which is another dimension I'm showing to you right now, you can do comparison analysis and risk analysis against key parameters. You can work out optioneering exercise for temporary works if you're an EPC contractor. You can justify really the site selection if you're an operator. And for an SMR developer, this would allow you to secure the standardization that you need for the fleet deployment across multiple sites. And again, inside this twin, I'm capturing not only how the plant would look like with all the interactions between stakeholders, but what is the impact in terms of logistics, resources that I need. And this is a collaborative tool as well. Obviously, the twin allows a great buy-in and communication exercise between all the players, because you can interact, you can understand the same reality, and you can take, again, decisions early stage and de-risk the project. Now, we've talked about MBSE, system of system, AWP, 4D simulation. What we need is a bit more of AI and data science on top of that. Why? Because that would be the way where we can bring contextualized insight that would help take the right decisions. So on top of this model that are repeatable, that are scalable, and that are consistent and allowing for the scaling up of nuclear projects, if we bring predictive intelligence and AI, data science and AI in those twins, you have the capability to address one of the major challenges that we all have, is that the data is today very siloed across the stakeholders of those nuclear projects, across the life cycle, very fragmented. And how do you make sense of that? That's how the technology and where the technology can help. Aggregating data from different sources of information across the supply chain and transforming this into, again, contextualized insights and that would lead to actionable decisions. That's the main value of, again, virtual twins approach in those phases of preparation of projects and making sure that we are doing it right for the first time. So we can go beyond what most of the people are doing, which are mostly a probabilistic analysis, you know, in terms of risk. So a lot of Monte Carlo is used at the moment. We can simulate impact of design, supply chain, you will see that. And we can ensure the readiness of activities before we start. Because we need to start on time. This is something that has been said on the plenary yesterday. How do we make sure we start on time? And how do we make sure that the progress is monitored in the right way and that we are delivering according to plan? So I'm going to show you how data science and AI are bringing this into play within the twin. Coming back to the scheduling of what I call prerequisites, let's say, of the work. These are all the tasks that I need to have secured before I can start an execution. This is my planning. I can do dependency risk monitoring thanks to AI capabilities embedded in the twin. And I can do predictive delay analyzer, meaning I'm really focusing on all these prerequisites, the sequencing that I've foreseen at this stage. And again, it's before any activities. And I'm identifying critical areas. And this is ingesting the knowledge and the lesson learned from the past. Because if I want to replicate, I need to capitalize. I need to maintain the learning curve. I need to increase that learning curve. And I need to secure the improvement. So here what you see is I've got the capability within the twin, aggregating data from different systems to have an understanding, exhaustive, holistic understanding of the status of the work packages. Which one are at risk? Which one are less at risk? And based on the past, I can leverage my AI companion as a decision copilot to help me understand where should I put my focus? Where is the critical areas within the schedule? And at this AI companion, when he's advising me to look at specific work package, I can even ask him to suggest recommendations of improved scheduling scenarios. Why? Because he's consuming data from my own knowledge and know-how from previous projects. So he's really giving me insightful recommendation that would allow me to take the right decisions. Here what you can see is another example of that. This is what we can call a readiness cockpit. So do I have everything I need before I can start an activity on the ground related to engineering, documents, procurement, areas available, or resources also available. But I can look at that information in the context of the 3D. So everything that you see here is a massive and complex volume of which was siloed and fragmented data that I'm now represented into contextualized insights connected to the 3D that you can see on the right. And here again, I can ask the AI companion to help me make recommendations and support. For instance, looking at this pump, I'm asking him what are the equipment that were supposed to be installed and that are in quarantine on hold. This is this pump. Okay, but now what shall I do? The best of the twin is that it not only gives you contextualized insights, it helps you take the actionable decisions out of it. So now I'm asking him to suggest me and identify me a similar pump available on site that I can use in replacement of that one, because this was the critical task that I should have been doing at the time of the project. And he can do that because, again, previously he had the knowledge of all the model and the equipment and the system of system that was required. So the twin knows which pump should be installed at that specific area, that specific location, and it can help me suggest an alternative scenario. Now we've spoken a lot about de-risking. optimizing in the virtual world before we start the works. You've seen the value of data science and AI in terms of also monitoring the progress on site and being reactive in the decisions that we need to take. I think we need to speak now to how we can shift from the traditional one-off construction to the industrialized delivery on site. And for that, I would like to invite with me on stage our partner, Langewerk, a pioneer company, UK-based in engineering and construction, delivering major infrastructure projects, specifically in nuclear, because Langewerk is actively present in delivering the works on HPC, Hinkley Point C, and Sizewell C tomorrow, and also really involved in the SMR delivery projects preparation that are happening across the world. So, Adrian, you're here because we share a common ambition. We share a common ambition that make digital innovation a catalyst for transforming the way we deliver those major infrastructure projects, and maybe revolutionizing how a nuclear construction should be tomorrow, and leveraging the virtual twin technology out of it. So, Adrian, major project executive for Langewerk, please tell us what you've achieved so far within Langewerk, because I think you're very advanced in terms of embracing this digital innovation, what the value you see through it, and maybe how that is serving you the future ambition that you have.
Absolutely. Absolutely. I hope you can hear me okay. It's a great pleasure to be here, and thank you for the invitation and the opportunity to talk about where we are on digital, but importantly where we go next, and to look forward in collaboration with partners. So I'm very excited to be here. I only have a few minutes, so I'm going to canter through very quickly what is a very big subject, but hopefully I can give you a flavor. Langewerk, many of you will know, we're a UK and Australia-based construction firm, privately owned. I think probably notable for the early investment around modern methods. I think we're a pioneer in modern methods of construction, and also probably less well known, but around digital as well. We work across a number of sectors, including nuclear. We are a key part of the Hinkley Point C project in conjunction with Bylaw, as part of Bylaw in conjunction with Bouygues. We're a member of the Civil Works Alliance on Sizewell C, and we're also working on SMR. So nuclear is a really big market and focus area for us, but we also build other products as well in healthcare and science, and also in sports. There's the Everton football stadium, which to date has been our most digitalized project, so we're really proud of that. I'll talk about Everton for a brief moment in a minute. So I think what's different about Langewerk is the fact that we own a lot of our supply chain. We're very vertically integrated. We own a lot of our subsidiary businesses. We own all our temporary works, all our crane fleets, all our plant equipment. And we also own and we set up large factories. This is the one in Worksop in the north of England, where building products, civil products are built in a factory environment. We also have a factory that does MEP, MEH modules. And we also have, it was talked about a lot yesterday in some of the presentations, a reinforcement facility serving Hinkley in Avonmouth. Our mantra is really 70, 60, 30. Three numbers for us are really significant. And this is what we try and do in all our projects. We try and build 70% of a project off-site in a factory environment. And that clearly has advantages in productivity, in quality, in all sorts of areas. As a result of that, we can take 60% out of the workforce on site. And obviously for the people doing that work, that is a transformational experience. You know, they're undercover, it's much safer. The facility can be nearer their home. It can open up an opportunity for people. And of course, it takes a massive load out of the site as well in terms of coordinating lots of people getting on and off and all of that entails. In terms of raw benefit, we also, as a result of those, strive to achieve a 30% reduction in schedule. And we're demonstrating that. We've proven that across multiple sectors, and we're now proving it in nuclear. And that's really exciting because that's 30% schedule, but it's the certainty around that schedule as well, which is equally compelling. It's not always 30%. It could be less. It could be more. It depends. But that's the number that we strive for. And here's the proof point. Some of this was talked about yesterday. These are some of the civil modules. Here's a 170-ton mega block on Hinkley Point C, which was recently installed. We'll see MEP modules here on the top left. And if we focus on this image, that's one of the big tanks. And if you look carefully, you'll see that's a combination of reinforced concrete, so heavy rebar, prefab. There's a stainless steel liner in there, but also all the temporary equipment and all the temporary lift equipment there is really significant. And I think what's interesting is to compare that to the digital model, because everything there is modeled, including the temporary works, including all the lifting equipment. And that does two things. That drives the design coordination, it declashes the design, but it also enables the 4D simulation, the 4D planning. It allows us to get absolute certainty of how we're going to install that and have confidence it's going to fit and everyone knows how it's going to be installed. So really the critical link here is that digital enables modularity, but also changes the nature of civils as we know it. These are engineered, manufactured products, and they have enormous amounts of digitalization and data associated with them, which we can then use in the world that Audrey just described. I'll drill into that just a little bit more, conscious of time. So we build from models on site. We do digital sign-off on site using tablets. And we have a range of capabilities as well. There's some of many examples. Site control, production dashboarding, starting to use AI for schedule optimization as well. That's really exciting. And I'm going to talk about 4D planning just for 30 seconds. And back to Everton. This is the immersive studio we used at Everton. 3 screens and one on the floor that are touch screens. They play a virtual rehearsal of the most comprehensive building and temporary works model that we think's ever been created on a UK construction project. We've got the logistics model. We've got all the project control information. As a result of running this capability in collaboration with the client, with the suppliers, with all our subcontractors, that's the major reason that this project was delivered on time. In fact, it was delivered a day early, and it's on budget. So that, for us, was a very powerful proof point of get digital in strategically, in collaboration early, drive it through end to end, and incredible results can happen. And for us, that's exciting. And as we look at nuclear, that's really exciting. Of course, that's a journey. As many of you will know, huge amount of digital technology, AI, but a lot of it is in silos. It's fragmented, doesn't all speak to each other. So what we look at is what is end-to-end digital delivery? You know, how do we take some of the learnings from other sectors in managing digital continuity? We can transform the workflows, we can transform the information flows. That isn't a Langer Rourke or a separate contractor exercise. That's a collaborative exercise that is done in a value chain, best for project. And that is genuinely transformational. There's an example of one of the workflows that we look at. Sorry, let me just go back. And if we look at that in terms of where we are on the journey, digital construction, Hinkley, as we move forward into the current generation, end-to-end digital delivery is what we're focused on. But there's a future world around SMR, which we're looking forward to and we're excited by. And we're excited by for a number of reasons. One, much higher level of automation, standardized products, standardized process. There are many of them. It's a fleet. So we have to work out how we build concurrently multiple fleets in the UK or in multiple countries at the same time. And that opens up the opportunity for us for an industrialized construction platform, which takes us into the world that Audrey described earlier. I'm probably out of time, so I can't talk to these points, but yeah, this is what we see as the next chapter. Thank you very much.
Thank you, Adrian, for this testimony. Just last word as major takeaways of what we've discussed today. So virtual twins, I hope you've understood it's not a digital tool, an additional one with respect to what we have already. It's more a digital backbone that would allow us to transform from a traditional siloed, fragmented delivery model to an integrated, orchestrated, end-to-end digitally enabled program. And combining the best of what's already available in terms of MBSE, again, SOSE, AWP, what we learn from other industries, especially manufacturing in the DFMA approach, and that Adrian has just illustrated, and leveraging what data science and AI can offer today, we can unlock significant outcomes and tangible outcomes for the project and for nuclear delivery tomorrow. So that's what we wanted to share with you today. Thank you for your attention. Just mentioning that we have a stand in FO21, so you're very welcome to have a deeper dive on those virtual twin experiences that I share with you today. And Adrian and myself will be, of course, available for further questions. Thank you for your attention. Thanks.